Hi, 8th graders. Today we're going to start on Unit 2, Part 1. This topic is all about acceleration. So we're into Newton's second law, which we're going to break into pieces, and the first part is understanding the idea of acceleration as a concept. Like always, you're going to need your notebook, where you're going to put notes on the left and your practice page on the right. From your warm-up, you should have read the article and answered the 3 questions in the Google form. If you haven't already done that, please pause this video and go back and finish that first. If you have already done that, let's quickly go over the answers. So acceleration, according to the article, is a change in velocity. But there are a few ways that you could have stated that, so I'll look at your answers on my own. For the second one, what is an example of something that is moving but not accelerating? That could be a lot of things. So as long as its velocity is not changing, that's an example of something where the acceleration is 0, but it's still moving. So for example, a car going down the freeway in a straight line, just driving down the freeway at a constant speed, or a bird flying in a straight line. The straight line thing is an important part because turning is actually a form of acceleration, because if acceleration is a change in velocity, if your velocity has a direction and you change the direction, that's a form of acceleration because you changed the direction. The last one is hitting the brakes a form of acceleration? The answer is yes. We'll get into it more in just a minute here, but that is a form of negative acceleration. So your velocity was a big number, now it's a small number, you changed it. So acceleration is any time you change velocity, either its direction or its amount. The objectives that you have for today look like these. The first one is to be able to describe the 3 types of acceleration, which we've actually already talked about already a little bit. Objective number 2 is to calculate acceleration when I give you 2 other variables, and then use acceleration or describe acceleration in a table and a graph. So these are the 3 things we're going to look at today. First thing that we need to do is define it. So on your notes side, there are a number of things that we're going to be putting over there. You may need more than 1 page for this today, but you need to have everything that's on my screen. So acceleration is a measure of how quickly velocity changes. And the 3 types we're going to look at are on your screen, both in words and in pictures. I strongly encourage you in your notes to have both. Have some words and pictures. So the first one is the most obvious one. You're speeding up. You're starting out slow and you end up going fast. That's the most obvious form of acceleration. Usually people are pretty good with that. The next one is slowing down. It's just the opposite. You start out fast and you end up going slow. That one's usually pretty good for people too. The one that tends to be the trickiest is this one, changing direction. If your direction and your velocity is this way, and then you turn it to be that way, that's a change in velocity because you change the direction. So you could be going 10 meters per second north and turn to go east and still be going 10 meters per second. That's a form of acceleration. Basically, in yellow is the thing that you need to take away. If the velocity changes in either its amount or direction, that is the definition of acceleration. So let's take this first example, speeding up. If you are speeding up, let's say that you've got an object that's at time 0 and velocity 0. On your notes, you're going to need a few rows to show these examples. We're going to keep track of both the time and velocity. This is going to come in handy when we start graphing here in a few minutes. As you're speeding up, let's say at time 1, now your velocity is 5. And then at time 2, your velocity is 10. So because your velocity is changing, you're covering much more space in between each one of these spots. And then at time 3, your velocity is 15. Acceleration is adding to velocity every second. So that's if your velocity is changing, that's acceleration. Notice we went from 0 for velocity at rest to 5 to 10 to 15. So we are adding 5 every single second. The next one to talk about, of course, is slowing down. So let's say at time 0 on our stopwatch, the time says 0, we're moving at 15 meters per second. A type of acceleration of slowing down, we could also call that deceleration. We're going to be taking away from the velocity every second. So because it started out going fast, it's going to cover a whole bunch of distance in the very first second, but now we're going 10, we're taking away 5. In the next second, we're going even slower, we're taking away 5 again, and in the last second, we're finally back down to 0. So in this example, acceleration is subtracting from velocity every second, but it's still a type of acceleration. We just sometimes call it deceleration. So far we've got adding to velocity and subtracting to velocity. The last kind is just changing the direction of the velocity. So let's say we're going 0 meters per, or at time 0, we're going 10 meters per second, but we're going at this like down into the right direction. And as we progress through this car's trip, its velocity was going down into the right, then straight to the right, now up and to the right. This is the last form of acceleration, and it's turning velocity every second. So we have adding to velocity, subtracting from velocity, and turning the velocity. These are our three types of acceleration. So from our last unit, hopefully you remember that we use plus and minus, or positive and negative, in order to show direction. So if something has a positive number, that means that it's usually going to the right or up or whatever you've defined to be the positive direction, and the opposite is true for the negative also. So let's go back to those examples that you should already have as pictures in your notes. We would say that this first one has a positive acceleration, and you know that acceleration is positive if it's adding to the velocity. So we started at 0 and ended at 15. We were adding 5 every single second, so we would call that a positive acceleration. So just like velocity, acceleration can be positive and negative too. Acceleration has a direction. If it's adding to your velocity, we would say that the acceleration is positive. Flipping that around for the other car that we already talked about, this one should also already be in your notes. This car has a negative acceleration, and we call it negative if ever it's taking away from the velocity. So we started at 15, we ended at 0, we were taking away 5 every time. That's a negative acceleration. Here's the equation. You will definitely need this on your note side. I would recommend finding a highlighter, putting some highlighting around it, maybe color it in. This is going to be an equation that we're going to use a whole bunch. At this point, I think we're up to about 5 equations so far in physics, so we are adding to the list. The good news is that we already know about velocity, and time is usually pretty good for some folks. The only thing that's different about this is how we're using them. And there's this little triangle shape. So if you've never seen this in math before, you need to know that this thing is called a delta, and it means change in Greek. So here's what this equation is telling us. It says that your acceleration, how much you're speeding up or slowing down or changing your direction, equals however much you change the velocity divided by however much time passed. Another way to write this looks like this. It looks a little bit scary at first, but it's really not too bad once you've practiced with it a bunch. So I'm just restating the same equation. Here's how we're going to use it sometimes in this class. So acceleration equals, if change in velocity is however much you ended with minus, like how much passed in between your start and your stop, it's just a subtraction problem. So this is how we could expand that out. It's velocity final minus your starting velocity, or velocity initial, divided by how much time happened. The units that we're going to use for this are the same as before. For our time, we're going to stay with seconds. For our velocity, it's still meters per second. It does have a direction since velocity is in here, but we're just going to use positives and negatives to tell our direction for this class. For acceleration, it's got kind of a silly at first unit, but once you understand what it means, it actually makes a lot of sense. So the units is meters per second per second. You would say it just that way, meters per second per second. You could also say meters per second squared, and it looks like this right here where my mouse is. Both of those are totally fine, and they mean the same thing, meters per second or meters per second squared. Here's what that means when you break it down. If I recolor them so that meters per second, that's our velocity, and that's our time in red, what you're really saying when you're talking about acceleration is how much did your velocity change, that's the blue part, every single second, or how much did your meters per second change every second, meters per second per second. That's what you're really talking about when you're talking about your acceleration. This equation also has a handy triangle, just like some of our other equations. This should also go into your notes so that you can solve for any part of the equation. If you want to solve for how much the velocity changed, that's on the top part, you would just do acceleration times time. If you wanted to solve for time, you could cover the t, and you would get change in velocity divided by acceleration. And acceleration, of course, is velocity over time. So let's do a calculation example using this equation. Let's go back to the car that we already drew. the car that started at time 0 and traveled for 3 seconds and was changing its velocity all the way. So for this one, we're going to start with our equation. Acceleration equals velocity final minus velocity initial over time. Substituting in the numbers, my final velocity was 15. That's what it was at the end of the problem, so that's what goes in first. My starting velocity was 0, so I got 15 minus 0. And the total time that passed was 3 seconds, so that goes on the bottom. So once you take 15 minus 0, which is of course 0, divided by 3, you get 5 meters per second per second. Now let's take another example with a car that isn't starting at 0. So this car is starting at 8 meters per second, and it's going to speed up to 64 meters per second. And it's going to take us 8 seconds to do this. We can still use the exact same equation, and that's velocity final minus velocity initial over time. In this equation, or in this example, we started at 8 and went to 64, so our final was 64. We're going to do 64 minus 8 divided by the 8 seconds. When we throw that into our calculator, 64 minus 8 divided by 8, we'll get 7 meters per second per second. Please pause this video and add any of these examples to your notes if you haven't already. Now we're going to do an example with negative velocities, and we're starting with a car that isn't at rest. And we're not going to end with a car at rest either. This is going to have all non-zero velocities, just to take all of the challenges together into one question. We're going to start with the exact same equation, velocity final minus initial over time. In this example, our final was 19.5, and our initial was 30. So we're going to plug those into our equation. It took us 3 seconds to do this trip. We have to do the subtraction first before we do any division. So 19.5 minus 30. Hopefully you're thinking, wait a second, we're going to get a negative number. And that's exactly right. We should expect that because we have an object that is slowing down. We are taking away from the velocity every single second. So we should have a negative number. So we get negative 10.5 divided by 3. When we put that into our calculator, we get a negative 3.5 meters per second per second. Think about what that means for a second. We're taking away 3.5 from the velocity every single second. That's what acceleration tells us. How much are we changing the velocity? Now we're going to tackle one of the most challenging types of questions that we will cover in this class. It's one where we have to calculate the starting or final velocity. So instead of calculating acceleration, we're going to solve for one of these velocities. But the good news is that the equation and the math is all the same. So we have a bike rider that was going 1.5 when they reached the top of a hill. So at the top of the hill going 1.5. They're going to go down the hill and accelerate at 0.75 meters per second every single second. So we're adding to the velocity. We should have a bigger velocity when we're done. And the bike is going to do this for 4 seconds down the hill. Our job is to figure out how fast were they going at the bottom. If you immediately can see how to just add this amount to the velocity, that's awesome. I'm glad that you can see that, but I also need you to know how to calculate it for when the numbers get more complicated. So we're going to practice with the equation. Same equation, velocity final minus initial over time. We're going to plug in the stuff that we know, except this time we know the acceleration. So we're going to put that in, 0.75 on the left. And then on the right, we don't know velocity final, but we're going to plug in the other two numbers. Now, order of operations says in order to get to this v, we have to get rid of this bottom part first. We have to multiply first because this is division. And to undo it, we have to do multiplication. So we're going to multiply both sides of this equation by 4 in order to get this off the bottom. So when we do that, we'll get 3 equals velocity final minus 1.5. We got rid of that 4 on the bottom. Now we have to get rid of this minus 1.5. So to undo that, we have to add 1.5 to both sides of the equation. When we do that, we're going to get our velocity final at 4.5 meters per second. So we've just found out that the bike at the bottom of the hill is going 4.5 meters per second. Now it is your turn to do a little practice. So on your practice side of your notebook, I need you to try these 4 questions that are on your screen. So you need to pause this video. When you're finished, there's another video in Google Classroom where I show you all of the answers. You don't have to watch the whole thing. What you can do is grab the little slider and scrub the video to the spots where I show you the actual answers. And if there's anything wrong, then you can rewind and actually watch and see how I did it. The goal here is for you to learn. Don't just check your answers and see if it's wrong and then move on. If it's wrong, you need to go back and watch how I did it. So pause the video now and try these 4 questions. If you're still watching, you've tried the practice questions. Here's where we're at in terms of our objectives. We've talked about how to describe the 3 types, positive, negative, and change in velocity. We're not going to do any calculation problems with the change in velocity ones. You just need to know that that's a type. For the second, we calculated acceleration when you were given velocity and time, and we even calculated one where you had to solve for a velocity, so we did a little extra there. Now it's time to describe acceleration using a table and graph. We've already done displacement time graphs, so this should feel a little bit familiar, but acceleration definitely adds another layer to that idea and that topic. On a fresh piece of paper, you're going to want to start a new notes page. Since we're kind of going into a new topic about graphing, this is going to take up some space, and if you're running out or if you're already cramming everything in, you'll keep yourself more organized by starting on a new page. I need you to have the table that's on my screen jotted down into your page. There's also going to be a picture and 2 more tables as well as some graphs. We're going to be doing a bunch of things. So pause the video, get this first one jotted down. If you're still watching, I want you to next make a prediction of what should be in these empty boxes that are covered up. So if you haven't already, pause, make a prediction of what you think it's going to be, and then when you come back, we'll show you. So this is an object with a constant velocity. It's going 25 meters per second, maybe just cruising down the road. Since its velocity is constant, that means that acceleration is 0. We're not adding or subtracting from the velocity every single second. So it's 0. However, because it's moving, we are changing how far it's going, its displacement. So if it starts at 0 and its velocity is 25, that means we're adding 25 to how far it goes every single second. So after 1 second, we're at 25, 2 seconds, 50, 3 seconds, 75. Now let's talk about a negative acceleration object. So we have an object that's traveling at 30, and we're going to be slowing down. We are decelerating. So hopefully automatically in your mind you're thinking, okay, negative acceleration. We are taking away each second. So here is the table that we have for slowing down. Let's say at time 0, we were going 30, just like the picture, and we are going to be subtracting from our velocity each second. Jot this one down on your notes and see if you can predict what should be in the boxes this time. Let's start with acceleration. So if you notice, we are subtracting about 3.5 each time, each second that goes by. So our acceleration is a negative 3.5. We're taking away 3.5 every second. The displacement is also going to be shrinking. So at the beginning, it was going fast compared to the end of this little trip. So at the beginning, it was covering more ground per second. And each second, we're also adding to the displacement. So at first, these numbers might look a little strange, but let me explain. So in the first second, we covered 28.25 meters. That's about this space right here because it was slowing down. And then each second, we were adding to our displacement because the car was getting further and further away from the starting. But the amount that we are adding is shrinking each time. The last example that we need to look at is speeding up. So this is the last table that needs to go on your paper. Let's say that we have an object that was starting at 0 for a velocity and ended at 10.5 for its velocity. Pause the video and see if you can predict what the numbers should be like on this one. Let's start with acceleration again. So this time we're adding, and it looks like we're adding 3.5 each time, so that's our acceleration, plus or positive 3.5. And since we're adding to our velocity, we're covering more ground each time, and that car is getting further and further away. So here are our displacements as well. So in the beginning, we don't cover much ground because that's when we were going the slowest, but we keep adding a dramatically increased amount of displacement each time. On your practice side, before you move on, please do a quick stop and jot. Out of these 3 tables, which one do you think is the most confusing for students, or even maybe for you if you are feeling confused? And tell me a little bit about why. I want to be able to read these to try to address any confusions that you might be having at this point once I collect your work. So pause, and on the practice side, please do a stop and jot. The next part is to look at these graphs. So for this part, all I did is I took the tables from the previous slide and I've just extended them out for more seconds. So you have the first few seconds of this data. You do not need to jot down the rest on my screen. I just wanted you to see it all stretched out. But it's the same exact experiments or objects from the last screen. I want you to be thinking about what these graphs should look like. So I'm going to show you the first one, and you're going to make some mental predictions for the others, but these graphs should also show up on your notes page. So here's the first one. So I've graphed displacement, velocity, and acceleration on the same graph so that we can compare these three things. So in this first one, our acceleration was 0 because it was just an object moving at a constant rate, wasn't changing how fast it went. So you'll notice the yellow line stuck down here at 0. For velocity, we also have a flat line because it's not changing. And flat things are things that don't change. So we have this flat line going along at 30. But our displacement does change. As you drive down the road going a constant speed, you're going to get further and further away from wherever you started. So that's our displacement line in blue. Again, this should be on your paper as well as these notes underneath. So for a constant velocity graph, the displacement slopes up, your velocity is flat, and your acceleration is flat at 0. This is a good reminder to have for this type of graph that you'll see often. Now that you've seen what the constant velocity one looks like, see if you can make a prediction for what the slowing down graph should look like. Think about what the acceleration, velocity, and displacement lines should be like. Pause the video and make a prediction. Let's see if you were right. So for this graph, it should look like this. This time our acceleration was -3.5, so you'll notice the acceleration line is just a little below the 0 line, but it's still flat. Our acceleration was the same every single second. We were always taking away 3.5. Our velocity was constantly being reduced by the same amount each time, so we have this negatively sloping line going down. For our displacement, because our velocity was shrinking each time, we were covering less and less and less ground every second because we were slowing down. So our displacement continues to get further away. It's still driving away from us, but the amount that it gets reduced is taken down each time, so we get this curved graph. The things to realize about this graph that need to be added to your notes are these. Your displacement is a curved down line. Your velocity slopes down, and the acceleration is still flat. Now for the last graph. This time we're going to do speeding up. Again, please pause, see if you can predict what this graph should look like. Here's what we've got. For this graph, we've kind of got the flip of our slowing down. The acceleration is still at a flat line because we're accelerating at a constant amount every second. Our velocity is growing by a constant amount each time, so we've got this gradually increasing line in red, and then the amount of displacement, or how much ground we cover, is getting greater and greater and greater every second, so we get this curve as it increases over time. The things to realize for this one is that we have a curved up displacement line, our velocity slopes up, and the acceleration is flat. In order to get some practice with graphs, the next place you need to go is this interactive that's linked in Google Classroom. It's the Physics Classroom link. Once you get there, you'll notice this little window that's all super tiny. If you click on the arrows on the top left, or you can click and drag and stretch it out, it'll make it much more user-friendly, and here's how it looks. You do not need to log in using your name. I honestly don't care what name you choose. But once you click Start, I need you to choose the apprentice level questions to start. If you feel like they're too easy, you can go back and begin one of these other higher level ones, but you're going to start on the apprentice level. Here's what it's going to show you. They're going to show you this graph on the left of a displacement or position time graph, just like we were doing in the last unit. Your job is to predict or come up with what the acceleration or velocity time graph should look like. Notice it's got a plus and a minus side. You'll check your answer each time you choose a graph. You can click over on the right side to choose different graphs, and you'll check your answer. If ever you need help, there's a Help Me button where it explains the answer for you too. But try all 4 of them, and if they're too easy, go to the next level. To close, I need you to go to the other Google form that's in Google Classroom, the one that is called Closure. These 3 questions will be found in that form. Then you are finished with the lesson. Don't forget to attach a picture of your practice page. Ready to go.